All right, I think we have a quorum and we can begin. Um, Good day, everyone. Thank you all for joining this Tech Talk, um, proudly brought to you by IEPNG and Tedi. The aim of this Tech Talk is just to share knowledge across PNG and just to encourage everyone to be critical thinkers and learn from each other. Today, we are fortunate to have David Ryong from Tedi from the hydrogeological team in Tedi. David, we look forward to all the great work you guys do, and we look forward to all the lessons learned and how we as engineers can continue to be critical thinkers and help PNG move forward. So, David, I'll give this to you to take on. Thank you.
Thank you, Brian. Uh, Thank you, everyone. Yeah, firstly, I would just like to thank IEPNG. Yeah, the initial discussions between IEPNG and the OTML team was initiated by my former boss, Matthew Montai, who was the soup for our OTS team here in POM, but he went to Sweden, so I'm the only one doing the presentation today. Yeah, my presentation will be on ground support and depressurization drilling in Octary mine. Uh, Apologies from Dauba. He's a bit busy, so he won't be joining us with this presentation. Yep. Thank you, IEPNG, for providing this platform. It's a good initiative by IEPNG with all technical experts around PNG for us to come together and share this our technical knowledge on what we carry out in each of our respective fields. Without further ado, I'll continue with my presentation, if okay with you all.
Yep, David, thank you. You can begin.
Okay. So, yep, to give context on some of you who might not be familiar with where I work, Octady mine is located, uh, yeah, 815 kilometers northwest from Port Moresby, near the border of Indonesia and Papua New Guinea. Um, Octady mine has been in operation since 1982. Production began in 1984. So the mine is 45 kilometers from the township. So that's basically where we used to work. Now we relocated to Port Moresby because of yep, Octady is expanding. Moving on. So just to give context on Octady's pit, the mine pit. Octady is situated at an altitude of 1,500 to 2,000 meters above sea level. It has a very extreme hydrogeological environment there, with annual rainfalls of 10 to 13 meters per year, and it's recognized as the wettest operating mine in the world. Um, yeah, with all that rainfall we get, it creates a operational hazard and a very unique engineering challenge to most of us working in Octady. Um, the deposit is a porphyry copper and gold system deposit, mainly consisting of monzonite porphyry, MP, and monzodiorite intrusives, primary country rock, Yarrow siltstone, Pingyang siltstone, and Darre limestone. major structures, Taranaki Trust Fault, Basal Fault, and Parrot Big Trust. So this is just to give the context of the geological makeup and geotechnical makeup of the pit. That way, when we go into our presentation, you would understand more why the geotech and the geological aspects are critical in ground support and depressurization drilling. So, of the mines, geotechnical complexity coupled with the extreme hydrogeological environment provides an extremely unique challenge to geotechnical engineers providing safe operations, mining engineers and geologists planning the mine's production targets. So, what is ground support? Ground support in large open pit mines. So, in there's ground support works that our civil counterparts usually carry out. Uh, in a mining environment, it's very dynamic. Most of the things that we do in the pit are not really built to last because when there's new deposits, we normally have cutbacks. So sometimes most of the walls are not um, final walls. So in mining context, ground support is any form of support, active or passive, either structural or geotechnical measures that are implemented on benches, rock faces, and walls to control rock mass movement, reduce risk of instability, immediate or future risks, and maintaining slope integrity on open pit slopes to achieve pit optimization safely. Importance of ground support in LOP mines. It prevents bench and interim failures, control raveling, toppling, and wedge failures, manage ground deformation due to seismic activities, protect equipment and personnel on production benches, optimize operation life for pit walls, ensures safe mine production and economic performance. So how do we determine if ground support is required on a bench? It all starts with the understanding of the geotechnical model, uh, geological model, and the geotechnical model. From early planning stages, um, from MTP and LTP stages, the geotechnical engineers identify during design reviews and identify and understand the risks and hazards associated with um, exposing weak rock masses, weak zones from the drilling data records and also from face mapping data that's captured in our database. Rock mass data is reviewed by the geotech engineers and they make the call um, whether to carry out ground support. During operations, operational geotechnical engineers make calls um, when there are unknown geological hazards that are exposed during mining. So that's some of the main reasons why ground support is carried out in an open pit mine. Okay, so this is uh, so these are the rock mass parameters for a majority of our lithological units in Octane mine. Uh, what I've highlighted in red are most of the lithologies that um, we mostly plan for ground support or we carry out ground support on. Most of the time, these are the um, rock mass domains where we encounter issues like what we've mentioned, raveling, wedge failure, toppling, all that. So determining the factor of safety um, in large open pit mine slopes for ground support. Uh, During the design reviews, mine designs are reviewed by the geotechnical engineers. The non-weak zones are assessed, and if the factor of safety doesn't meet the acceptable design criteria, ground support is recommended. During operational inspections, assessment from operations geotech engineers determine the potential of failures on slope and the possibilities and the ground support that is recommended for these failures. Um, so the initial assessments that are carried out and then the final assessment. So the initial assessment is when during the design review or the initial inspections, and then final assessment after the ground support is completed. We normally carry out the final assessment. So majority of the ground support that's carried out here in Tedi, the range is within, I've highlighted in red, majority of the ground support that we carry out with shotcreting, fiber reinforced shotcrete, and chain link mesh with fiber reinforced shotcrete. So this gives us a range of between 3 to 15,000 joules of the resisting force that's added onto the resisting force of the in situ rock mesh. So the different types of ground support carried out here in Octady, rock bolted mesh wire reinforced, fiber infused shotcrete walls, gabion retaining walls, soil nail tension wire, mesh wire reinforced, rock bolt tension wire, soil nail tension wire covered in geofabric, and mesh wire buttress fill, limestone boulders or competent siltstone, fiber infused shotcrete on walls, bench step out or wider beam widths, and rockfall fencing. So I've put active and passive on most of these ground support systems that we use. So active are the ones where that are actively reinforcing the walls, and the passive ones are the ones we use when there's already failure, but it helps as a passive resistance of that possible failure that's about to happen. So with rockfall fencing, we have passive there because it doesn't actively stop the rock falls, but it captures the rock falls as they come down. So I mentioned the design acceptance criteria. So in the table here, you can see these are the acceptance criteria for the factor of safety. So you have for temporary pit walls, 1.1 to 1.2 FOS, permanent pit slopes, 1.3 to 1.5. Here in Octady, we use 1.2 to 1.5. Critical infrastructures, uh, more than 1.5 or equal to 1.5. So just to give an example of the type of ground support that we use. So this is an example of a ground support we carried out back in 2022 to 2023. This was done in IEPNG. This was a pecan field area. You can see the pecan, majority of the field is within this area. And then you have all these alterations and oxidized weak siltstone on the outlayers. So within this red outlined area is the rock bolted mesh wire reinforced fiber infused shotcrete that we carried out. Also within that same area, we also did gabion retaining walls as tow locks for the beacon buttress. So after buttressing the walls, we did the gabion baskets to help with the tow lock, just to increase the resisting force. Um, so the one that we've outlined in blue, we used, since it was within field area, we used the soil nails to anchor the chain mesh, and then tension wires to hold down the uh, mesh wires, and then fiber infused or iron filing infused shotcrete. So this was a ground support carried out 2023 to 2024 up on the chasm crown. Um, we utilized rock bolts, tension wires, mesh wire reinforced, and iron filing infused shotcrete. So this ground support, basically the type of um, the type of rock mesh and type of structures that are running along that rock mesh. Also the beddings, as well as the context of the lithological context. These are the things that determine the different ground supports that we normally utilize in the pit. So these are just examples of the ground support works that we've carried out in the pit over the last 4, 5 years. Okay, to summarize our ground support works, the key benefits to ground support systems: they prevent bench and interim failures, control raveling, toppling, and wedge failures, manage ground deformation due to seismic activities, protect equipment and personnel on production benches below, optimize operation life of pit walls, ensure safe mine production and economic performance. Limitations of ground support works, the cost of budget required for the support system. So as you all know, the budget for any work or project is the most important thing. Most of the time, if the project is a or the ground support required is a strategic project that will impact life of mine in the long run, we normally carry those projects out as capital expenditures, capex. But if those ground supports are required for normal interim benches or operational benches, we go with our operating cost or operating expenditures. So depending on the impact of the project. Design life of the bench, that's also a limitation of your ground support. The type of ground support that you will be building or constructing, it depends on the life of the bench or slope that you are uh, planning to build your ground support on. If it's an interim bench, the ground support that you'll be building should not be one where it should over-engineered or overestimated cost of running constructing that ground support. If it's a final wall, then it's better to go with the ground support that's possibly over-engineered and has to last until life of mine. And then the third one is availability of equipment required for the job. So most of the time, we plan for the best, but the availability of equipment is one of the main constraints limiting work carried out in the pit. So we have to be realistic with what equipments we have when carrying out the ground support work, or when planning the ground support we're about to construct. And then lastly, the availability of materials required for the ground support construction. So that's something where procurement is something where we need to um, include in our plan. When you're planning a ground support, you have to know the lead time for the materials to arrive on site from the warehouse or from your suppliers. Okay, ground support systems are critical for safe operations in any large open pit mine, especially in Tedi, where we have high rainfalls, high pore pressures, complex geotechnical and geological formations, where juggling production with safety is a very complicated issue involving all stakeholders in the pit. So that basically brings me to the end of my ground support presentation. I'll be moving on to the depressurization drilling. However, if there's any questions on ground support,
Yeah, yep. David, probably one question for me. On the design life for the benches, how is that
yep,
like
yep,
calculated?
yep.
Like, is it
So,
through like, yeah?
yep. So with the design life, that usually comes from our LTP team. Um, so you have the overall pit shell that's given by the LTP long-term planning team, and then they're basically the ones who give us the life of mine picture, and then from that, the mid-term planning engineers they normally break that down to the 3 year to 1 year plans, and then they tell us that okay, so these benches are gonna be here for the next couple of years, for the next 2 3 years. So the benches that we are trying to do ground support on, if it's for the next 2 3 years, then we'll have to at least carry out ground support that's sufficient to resist any of the driving force in the slopes for the next 2 to 3 years. But if it's a final wall for life of mine, if it's 5 to 10 years or 15 years, then we'll have to go with uh, the best approaches possible. If it means we have to over-engineer it, then we get all the best equipments and materials available to construct the ground support. So basically, the LTP and the MTP guys, they're the ones who determine the design life of mine of those benches.
Thanks, David.
Yep. Nothing else. I'll move on to the press drilling. Bradley Valley, no questions. Okay, moving on. Slope depressurization drilling. Okay, what is slope depressurization drilling? Slope depress drilling in large open pit mines is basically um, drilling of horizontal drainage holes on slopes, both on surface and underground, purposely to reduce pore pressure within certain lithologies and structures in the pit or slope. What are the importance of slope depressurization in large open pit mines? They basically to optimize the pitch slope designs, enable safe cutbacks to achieve life of mine pitch slope designs, stabilizes moving slopes effectively depressurizes an unstable slope with high pore pressure showing signs of instability and movement, direct support for mine operations, enables safe operations in the pit to achieve production targets. So yeah, basically slope depress enables safe mining down in production benches. It also depressurizes the walls to reduce risks of wedge failures, raveling, toppling failures. Basically, majority of the failures that are impacted by pore pressure within the slopes. How do we determine if slope depressed drilling is required? High pore pressure readings, normally from high pore pressure readings in VWPs, OSPs, and other subsurface instrumentations, indicating possible trends of subsurface movements or possible failures. So basically, we have a lot of VWPs installed around the pit with OSPs. So they tell us if there's a recharge in the pore pressure or a drawdown in the pore pressure. Visible seepage on slope faces, sometimes addition boreholes in geotech drill holes indicate pore pressure in slopes. Active movement of slope due to high pore pressure picked up by radars, prisms, or subsurface instrumentations. So sometimes we have the radars picking up movements in the pit, and then the operation geotech engineers make the assessment, and then they determine whether if it's necessary for us to go in and depressurize the walls. Consecutive failures on slopes during high intensity rainfalls, usually after 2 to 3 days. Um, yeah, since Octet is the wettest mine in the world, the rate of recharge in groundwater, coupled with affected zone of relaxation, is shallow due to multiple drilling and blasting activities across the pit. They all contribute one way or the other to increase regional pore pressure and transient pore pressure, resulting in instabilities around the pit. So I'll define what transient pore pressure and regional pore pressure later on. So the geological and geotechnical complexity of Tedi creates multiple hydrostatic zones, confined aquifers, unconfined aquifers, throughout the structural stratigraphic traps within the pit. So we have trapped water above impermeable layers, which are patch aquifers or unconfined aquifers. Example, you have limestone Taranaki thrust contact or the limestone siltstone context. So this lithological context with the structure or the lithology context of a permeable rock mass like limestone, and then a impermeable rock mass like siltstone, they normally create a patch aquifer or unconfined aquifer. So you have a hydrostatic zone or a water table sitting above a impermeable layer. Water confined between impermeable layers, you have a confined aquifer. So you have a siltstone impermeable layer up here, and then you have siltstone down here, and then you have limestone in the middle. So majority of the time, there's structures running across where you get all the water from the surface infiltrations going into this limestone, and then it's confined within these two impermeable layers. Um, Water trapped by faults and bedding contexts. Yeru siltstone at west wall. We have the siltstone, Yeru siltstone beddings, and then we have structures in structures intercepting these beds. Majority of the structures that create the trap clay infill structures. So with the clay infill structures, they create the trap where the groundwater moving within the beddings trapped. So you can see visible seepages on the wall where the water daylights out of the wall. And then finally, we have localized water hydrostatic zones in the slopes or the pit walls. So these are basically weak or altered sections of the siltstone or the limestone where you have the rock mass acting more or less like a sponge. It's just holding the water and then there's no real outflow of that water. There's inflow, but it doesn't allow the water to pass. So how depressurization drilling impacts the stability of a slope? You have pore pressure is a main factor in slope stability assessment. Uh, effective stress, uh, which controls the shear strength, is equals to total stress minus the pore pressure within the lithology. This impacts pore pressure in major structures with clay fields and weak rock masses that display soil type behavior, which takes time to react to depressurization, but are responsible for majority of the major failures within the pit slope. Depressurization drilling strategies and methods. So basically, we have uh, 3 depress rigs up on the surface and 1 depress rig down in our underground dewatering tunnels. So we have 1 rig 5, which is a hammer. It utilizes hammer for drilling, and rig 9, which utilizes rotary drilling. Short-term for surface depress drilling, we have short-term slope depressurization, horizontal drainage holes, HDH holes, drilling short holes. Majority of the time, these short holes are purposely to target transient water in the pit. So transient water, most of the time, it's responsible for bench scale failures, wedge failures, toppling, all that. Most of the time, it's because of the transient pore pressure. So the transient pore pressure is within the zone of relaxation, 40 to 50 meters from the surface. Mid-term slope depress, horizontal depress holes, medium holes ranging from, so the short holes, they range from 50 to maximum 100 meters. And then for the medium holes, you have 100 to 250 maximum. And then the strategic depress drilling, the horizontal holes, long holes, those are from 350 to 450. Most of the time, we try to target the life of mine picture. So those depress holes, even with the cutbacks that will come into play, we still have those depress holes running after the cutbacks are done. For underground depress drilling, long term, long-term slope depress drilling for life of mine strategic project. Those are, as you can see here in Kaditri, sub-horizontal depress drilling long holes, usually 350 to 450 meters. And then you have mid-term slope depress. Those are sub-horizontal depress holes, but basically they are targeting bodies of water within the pit or within the lithologies that are identified. So, especially when you have those weak rock meshes or when you have patch water tables that we try to intercept from the underground. Key steps in carrying out depressurization drilling. So basically, with the data that we collect from our piezo's, the VWPs, the vibrating wireline piezometers, and open standpipe piezometers, the OSPs, also from our geological data, structure mapping, and the hydrogeology parameters that we get from carrying out slug test, um, packer test out in the pit or in the geotech drilling holes, just to get some data so that we can use this information for us to design deepest holes and get the correct targets. Otherwise, we'll be wasting money just drilling holes without intercepting um, the right targets. Target zone identification, that's basically what I've stated, based on pore pressure and slope geometry. A hole design, the diameter of the hole that you'll be drilling, the length, orientation, spacing, and the filter material that you'll be using after completion of the drilling. So normally we install PVCs, slotted PVCs covered in filter cloths. So that helps to keep the horizontal drainage hole uh, in the long run. Drilling methods, rotary, diamond, downhole hammer. Drain completion, PVC slotted casings with filter cloths, expected drawdown assessments. So after completion, we normally assess um, in our hydrographs from the VWP data that we um, get out in the pit. So as you can see below, this is a VWP that we've installed, GDH 1282 and GDH 1281. So both of them monitor the pore pressure within this sector of the pit. And this is a deepest drill hole plan that we've carried out and completed. So after drilling, we normally assess the hydrographs and see if there's a drawdown um, or there's a increase in the um, trend, the pore pressure trend. So a case study of deepest drilling stabilizing pit slope in the pit. Back in 2021, we had a multi-bench failure in FOOP 6. Um, we had tension cracks uh, being monitored up on the cutoff ramp, the drainage ramp. Um, they were dilating after heavy rainfalls, cumulative rainfalls of two, within 2 to 3 days. We have the bounding structures, uh, two major structures intercepting, creating a multi-bench wedge failure. It impacted production, halting production for, I believe it was for a week. And then for a week, we couldn't mine around this area. So yeah, we had some loss there. We had to step out. So step out is also passive form of our ground support. It helps us to stabilize any of these bench failures. Um, yep. And then we could not stabilize that multi-bench failure with our deepest drilling on the surface. So what we did was we targeted that area using our deepest holes in Cadi 1, the first Cadi that we did back in 2021. Um, we targeted the area in FOB 6, uh, mainly those two bounding structures, those two major structures. We targeted those structures, and then after depressurizing for a month, we saw an immediate effect of drawdown within the area, and then the bench or the wedge failure stopped moving since then. So that shows the effectiveness of deep press drilling, both surface and underground drilling. Okay, to summarize, key benefits of depressurization drilling. It optimizes the pit slope designs, enables safe cutbacks to achieve life of mine pit slope designs, stabilizes moving slopes effectively depressurizes unstable slopes with hypopressure, showing signs of instability, direct support for mine operations, enable safe operations in the pit to achieve production targets. Limitations of depress drilling. Drilling rigs are not always accurate in intercepting targets due to drill rods deviating from target locations. Normally when you have more than 150 to 450 meters of HD, H, yeah, depress drilling, majority of the time, they start to deviate, especially underground. And then for horizontal holes as well. With the HQ and um, the rods that we normally use, uh, most of the time they start to deviate from the targets. So that's why it's always best to know the drillers that you have on site. Make sure that you have competent drillers. Um, so when you see that you're not reaching your targets, the drillers can make the right calls to end drilling or to relocate. Reliability and contractor availability, effective utilization of time in pit. So a majority of the time, contractors are not really reliable in getting equipments up on time. Uh, and then when the equipment's available, the utilization of these rigs are not really effectively utilized within shifts. Reliability of data collected in the field from VWP, OSP, etc. can give false sense of increasing trend in pore pressure. However, drilling in the field will show no inflow in HDH holes. Yeah, so that's basically data QAQC for your uh, groundwater monitoring instruments. That's important. When you have um, false readings from instruments, sometimes you will think that you're having an increase in pore pressure in slopes, and then you'll be wasting money depressurizing walls that are basically dry. And then finally, in most projects, cost of the depress drilling is very high. So the cost is very important since the number of HDH holes are numerous. It is paid in shifts and not in meters. Unlike other drilling operations, it's paid in meters. For deepest drilling, we normally cover uh, 18, 18 to 35 kilometers of drilling per year. So that's a massive, yeah, number of holes that we have to drill in the pit and underground. So what we've done is we're basically paying our contractors in shifts. Depressurization drilling is effective when it is regularly monitored. Flow rates of HDH holes and VWP hydrographs, and integrated with hydrogeological models for groundwater drawdown, recharge, simulations, and geotechnical stability assessments. This is just a picture of our deepest drilling work in the pit, and then the dewatering pumps that are required to get all that water out of the pit again. Yep, that's basically the end of my presentation. Brian, any questions from the audience?
All right. Silence
Okay,
means everyone's fine.
no, no,
Um,
I have a question. Okay, David,
Yes,
I have a
Tom.
question. Yes, yes, I have a question for you. With
Yes,
with the data for the VWP as well as the HDH drilling, and
yes,
then we move down to the
yes.
surface water,
Yep.
and with the DNB and all the DC drillings. With all this data, do you guys create like phreatic surface to know your phreatic surface for the mine?
Yep, correct. So basically, with the phreatic surface helps us to visualize the water level in the pit.
Okay.
So yeah, basically, it just gives us a um, um, just estimation of where our water levels are in the pit from different sectors in the pit. Majority of the time in our hydrographs, we normally depend on the pore pressure to give us a accurate measure of what we're dealing with in the slopes. So the phreatic surface is good for us to get a visualization of the water level in the pit slope, but um, it's better to use your pore pressure readings to get a good visualization on the pore pressure distribution within the lithological units that you're trying to depressurize.
Okay. Thank
Hope
you.
that, yeah.
Yep. Okay.
Okay, thank you, Tom. Any other questions for deepest drilling or ground support?
David, I think we
Yes.
have a question in the chat.
Yep.
What softwares do you use at Octedi to do your models and designs and monitor hydrogeological and geotechnical conditions of the cut slopes of pit walls?
Okay, that's a good question. So in the past they were using UDEC to do the modeling for our groundwater models. Um, and then from UDEC, we went into for the last, I believe, 8 years. They were using ModFlow to develop the um, groundwater models. But yeah, the groundwater model using UDEC was more accurate model that was created. That's something that we're trying to look into right now. we're trying to create a numerical model using FIFLOW and Leapfrog to create a numerical model um, of the pore pressure distribution in the rock masses within the pit. So that's a project that we're looking into. Over the years, there's a lot of consultants that came in and then went out, and then most of our work were done by the consultants. So, as you know, with Dr. D now expanding, we're trying to upskill our own personnel to carry out this modeling. So that's basically what me and my team are doing here in POM now. Yep. I hope that answers your question.
All right. Do we have any more questions for David?
I have a question if no one's gonna ask anything.
Yep, go ahead.
Uh, Hi, David. Ketul here. Thank you for your presentation. I
Yep.
just have a couple of questions. The hole diameter, generally, when you drill,
Mhm.
what's
Yep.
generally the diameter of the hole?
Yeah, so we have PQ rods. We have PQ rods and HQ rods. The PQ rods are 112 millimeter. HQ rods around 90 millimeter. So those are the diameters of the rod. So basically the holes are within plus or minus 5 mils from those rod diameters.
All right, thank you. Next question. So the pipes or the drills are for specifically for pore pressure, not like heat pressure, right? Like I
Yep,
understand that in Lihir, there's it's in the pit, so I mean, dormant, is it dormant? Volcanic area, so they
yep,
drill holes to release heat pressure.
yep,
So just to clarify that,
yep,
is it like a dual function, or is it just specifically for pore pressure, to release pore pressure? That
yep,
pipes or that drills the holes that you make.
yep. So, yeah, good question. So the deepest holes that we drill, and then the drillers that we have, there's normally there's collars that we install on the drill holes. So these collars, let me see. Yep. So can you see these collars here? So basically for deepest holes, uh, we don't have uh, those annulus where it's required for geothermal uh, pressure release. For our deepest drilling drill holes, it's basically when you intercept water, you just have a high back charge from the hole, so it push backs on the drill rods, and then the drilling mast is basically designed in a way to um, uh, it has a high torque power to uh, push back on that or to absorb that pushback. So basically, it's the specification of how the drills are built, how the drills that the deepest drilling rigs are built. It's built in a way where it's purposely for deepest drilling. So you for geothermal drilling, it's specialized for geothermal drilling, and then for geotechnical drill holes where you have to retrieve the cores, it's a bit different from what we do. So we don't retrieve the cores. We only have the chippings that we look at, and then we log the chippings. But for the geotech drilling, they retrieve the cores from the holes. For us, it's just getting water out. I hope that answers your question.
All right, understood. Thank you. If it's okay, can I ask one more question?
Yeah, sure.
Okay, so just in one of your slides, you mentioned something about a relax zone or something.
Zone of relaxation.
Yeah, could you clarify
Yes.
on that, what that is, and is it
Okay.
as a for you as a geotechnical
Yep.
engineer who
Yep.
is concerned about the stability? I understand
Yep.
that
So
it's problematic for when we create tunnels and stuff like that. I understand that it's problematic for us. So that's my question. Is it problematic for you? Could you clarify on that?
yep. Okay. Yep. The zone of relaxation is basically so you have your intact rock mass and your disturbed rock mass. So basically, when you're drilling in a location where there's intact rock mass or there's no seismic activities that have disturbed the different rock mass that you're trying to retrieve, those that's that's basically a rock mass that's been undisturbed. For within the pit, we have a lot of disturbed rock mass when after drilling and blasting. So basically, what it does is it creates a zone of relaxation 40 to 50 meters from the surface. So that's basically the zone of relaxation where majority of the surface runoffs infiltrate into, and then when these surface runoffs, or this when these transient water, when they start to infiltrate into this zone of relaxation, and then it quickly recharges, or when it quickly increases the transient pore pressure, that's when you get bench scale failures within wedge failures, or any failures within bench faces and all that. So it's just a distant part of the uh, pit, the pit's in situ rock mass.
Thank you, David. I'm sorry for taking too much time. Thank you very
No,
much. That's all from me.
all good.
Thank you.
Uh, Thanks, David. Thanks, everyone. Just being conscious of time here. Chris, I know you had a question, but I'll do my best to get in touch with David to get that answer for you, and we'll do that. But David, thank you so much for this insightful tech talk. I know a lot of us here have little experience to geotech or have no experience, and thank you for the ease of presentation and the flow through it. To everyone, thank you so much for your time in participating in this. We aim to do this quarterly or monthly, and we look forward to your ongoing participation. And Chris will promise to get that answer for you. Thank you, David. Thanks, everyone.
Thank you. Thanks,
Thanks a
everyone.
lot,
you.
guys. Thank you, guys.